everyone, I'm back, and in this tutorial we are going to implement a Raycaster. There are a lot of cool tutorials out there on the internet, but this video I'm going to summarize and make all of them less complicated. I'm going to be using Python and Pygame for this project, but you can use any language with any library of your choice to implement this algorithm. I want this video to work for anyone. The entire code for this project is hosted at my GitHub. You can check that out in the link in the description below. So let's get started. Let's begin this chapter with this little GIF that shows how raycasting works in general. As you can see, there is a 2D representation and also the 3D, I should say, output of it. So what is raycasting? Raycasting was a technique that was implemented back in the 90s, used to create 3D games, like Wolfenstein 3D and Doom. Well, actually, there wasn't CPU power enough to create real 3D graphics back then. So, these games weren't actually 3D. They are more like pseudo 3D. So, how it works? Basically, let's imagine that this yellow ball over here is our player, and the blue squares are walls. Yeah, but all of this is going to become 3D walls, just like before. Simple. The player casts a ray until it finds a wall to hit. But not only one ray, it casts a bunch of rays. Just like this. Alright, now that the player casted all of these rays, we need to extract some information for rendering the walls into the screen. The way that it's done is by simply getting the distance of each line and using this to determine the height of a group of rectangles that are used to give the impression of 3D walls, when in reality the walls are basically some rectangles with different heights together. The thing is, the longer the distance of a particular ray, the smaller the height of a single rectangle will be. That makes sense, since the longer the ray is, the farther the wall is from the player. And to represent this, we need to make the rectangle smaller to give the impression of far away. There is also something we need to consider, which is this constant value here that I've called res. This is basically the width of each rectangle. I have called it res because changing it affects the resolution of the game. As you can see from this example, in a resolution of 30, the rectangles are more apparent, and the walls are not that obvious. Now, in a resolution of 20, you start to notice something. This is a resolution of 10, and hey, I guess that 4 is a good value for us. Remember that the smaller the width of each rectangle is, the more rectangles we need to render, costing us more CPU power. Well, each rectangle is associated with a single ray. So the higher the number of rectangles, the higher the number of rays that we need for each one. So the res determines the number of rays. We just need to pick the screen width and divide by the size of each rectangle, which is res. And this will give us the number of rays. Basic math. So, our current goal is to implement this 2D view of the raycasting. This is very important for us because this is going to tell if everything is working before we implement the 3D walls later. So everything I just taught you was a theory. Let's get into coding. So first thing I'm going to do is I'm going to create a settings file. Settings.py. This is where I'm going to store some constant values and stuff, and we're going to be using all of these values later in our code. So first thing I'm going to do is set the tile size. I'm going to say the tile size is 32. What is the tile size? Well, the size of our tiles. What are our tiles? The squares from our grid, you know, the walls and stuff. So I think I'm going to set up the rows, which I'm going to say 10. You can see from this that we are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, and I think 15 columns. So let's set this up. Also, we need to store everything in a window of a size. I don't know which size it's going to be, but it's very simple to figure it out. Every tile here has 32 by 32 pixels, so we can just find out by multiplying the columns and rows by the tile size. So let's set window width. It's going to be the columns times tile size. The window height is going to be rows times tile size. Simple enough, isn't it? There's also something I forgot to explain, which is the field of view, or just FOV. The FOV is basically the range that the player can see, and all the rays are casted from the beginning of the FOV to the end of it. Also, there's this line in the middle, which is the direction that the player is looking at. As you can see from this image, the FOV is measured in degrees, and we can change this value as we want later. So, knowing about the FOV, let's define it here. It's going to be 60 degrees. Well, but the problem is, all of the math functions are basically using radians as the default measuring system. So we need to convert this to radians. 60 degrees are going to be converted to radians. So how are we going to be doing this? It's simple. There's this little formula that we can use, which is we pick the pi and divide by 180. But the problem is we need to import math. So there we go. Now this is going to be 60 degrees but in radians. Now we can define the resolution also, which is going to be 4. You can define about 1, but I'm going to go with 4 because, I don't know, it feels enough, you know. Rays, which is going to be the number of rays. As we saw from that slide that I showed earlier, we can simply say window width divided by the resolution, and we get the number of rays that we are going to be casting. Now what I'm going to do is I'm going to set up a screen to be working here on Pygame. So let's import Pygame, and let's import the settings from which we just made. All of these settings are going to be imported, and we can define the screen to be pygame.display.setMode, and this is going to be the window width and the window height that we defined, while true. And we can say for event in pygame.event.get, if event.type equals pygame.quit, pygame.quit, and exit just to make sure it exits. Now it's time for rendering. We say screen.fill, we put a black, and pygame.display.update, and that's it. Let's see if it works. Let's run Python, and as you can see, there is a window, and with the proper window width and height, and we can close it very well. Let's go. Well, in this chapter we will focus on creating the map for our raycasting implementation. The map will serve us as the foundation for rendering the 3D walls later on. We will define the layout of the walls using a 2D array where each cell represents a tile in the map. So let's get started and do it. So what I'm going to do now is create the file for our map. This is the file where I'm going to create all the map code. So let's import Pygame. And let's also import all of our settings. Now let's create the class of our map. Let's create the constructor method. And well, this is the time we're going to be drawing our map. Kind of drawing it, I know. So I'm going to call it grid just to differentiate. But the thing is, this is a two-dimensional array, an array of arrays. And since we just tell that we're going to have 10 rows and 15 columns, it's good to have the same amount of rows and columns in our array. So I'm going to draw our map here. Just wait a second. So, well, this is our map. Every time we have the number 1, we have a wall. Every time we have the number 0, there is an empty space. There is no wall. But in number 1, there is a wall. So as you can see a little pattern here which draws our map. Now we need a way to render our map. Let's create a render method. Def render self, and we're going to be asking for the screen that we're going to be rendering. So what I'm doing here is I'm looping through all of the lists inside of the main array, the lists which contains zeros and ones. So these are basically all the rows that we have, and now I'm looping through each element inside of each row. So in the end of the day, the I will represent the row of each element, and J will represent the column of each element. What do we have here? Let's print to see what we got. So how are we going to be testing this? We're going to be creating our map on the main file, and we need to import the map, of course. There we go. So okay, so we just need to render this map, the screen. Let's see if it works. Here we go. It's printing here all of the coordinates of each tile. So we need a way to figure out the pixel coordinates for these tiles. I'm going to explain this in details in the future, don't worry. So let's go. We need to find the pixel coordinates. So we have a tile X, which is J times the tile size. Oops. What is happening here is basically the J is looping through the columns just like this, just like in a horizontal way, you know. It's the X value of each tile coordinate that we want to convert to pixel coordinates. So how do we do this? We just multiply by the tile size. For example, this tile here is the tile 0 in the column 0. So 0 times tile size, it's 0. So for this tile, the pixel coordinate is 0. But what about this one? This is in the column 1, and J will be 1, and times tile size, which is 32, the tile X in pixels will be 32. So repeat all of this for the columns, and also repeat all of this for the rows. I times tile size, and there we go. We have our pixel coordinates for rendering. Now we just need to check to see if the value that we found is 0 or 1, because if it's 0, we just going to be drawing a white rectangle, and if it is 1, then we're going to be rendering black. Let's get started. If self.grid in the position that on I and J, it's going to be 0, we draw a white rectangle. So Let's put this to be white tile, and we render it in the exact position like this. Tile size. This is going to render a simple square of tile size by tile size, the position that we just found. Let's do the exact same thing for if we find a 1 instead of a 0. Basically, we do the same thing but a little bit dark. And there we go. Now let's see if this works. So let me clear all of this and let's see. Ta-da! There we go. We have our map. Simple enough. But to give this a little bit more charm, just you see that it's a grid, we can just do we can subtract 1 at the size of the rendering, so we can actually see the grid being formed. So look at that. There we go. Much better, isn't it? So what we need to do now is to create a method that will tell us in the future if there is a wall in a particular position. So let's create it like has wall at, and we say like a position of X and Y. This method checks if there is a wall in a particular position. It returns true or false. But before we go further, we need to understand something first. We need to understand a very basic concept before going forward, which is converting pixel coordinates to tile coordinates. What does it mean? Well, suppose we have a map like this. The gray areas are walls and the white areas are empty. We know that our screen is made of pixels. So for this map, as you can see, each tile has 32 pixels for width and height. Alright, but all of these are just pixel coordinates. What about those tile coordinates? Well, tile coordinates, in the other hand, are related to tiles themselves. In this example, we have 5 tiles horizontally and 5 tiles vertically. Each of these numbers describe the position of the tile on the map. The first number is the column, and the second number is the row. For example, this tile is in column 2 and in the row 1. Okay, so far so good, but there's a big problem here. Let's imagine that the player is located here. The only information that we have at this exact moment of the game is the position of the player in pixels. Let's suppose that the player is located at 80 pixels in the x-axis and 59 in the y-axis. What if we wanted to know on which tile the player is stepping? We would need to make a conversion from player's position in pixels to find the tile coordinate that he is. To do this is very simple. We just have to divide the player's position with the tile size, which is in this case is 32 by 32. Doing all calculations, we would get this result here, which isn't exactly what we wanted. But wait a minute. Oh yeah, we can just ignore the decimal part and get the result we wanted. There we go. We can implement this super simple algorithm to our map class, which will certainly be used in the future to detect walls and collisions. So let's continue implementing this. We just need to return self.grid. We need to do something like this. Y. And I'm going to do this, which is something that Python offers, which is the equivalent of math.floor in JavaScript, for example. And it's very useful because it makes the code a little bit cleaner. So what is happening here is we are dividing the Y position by the tile size, and flooring it, which is going to remove the decimal part. But all of these calculations here are going to be floats, so we need to convert that to integers so it can fit inside of the array selector here. For the second part, it's int now the x we floor it dividing by tile size, and this will give us the row in the array and the column in the array that the tile is located, and that's it. So in our case, the map only has zeros and ones, but if you are implementing this and having more different kinds of walls, like 2 through 4, I don't know, you would need to say equals 1 or you know, everything. But in this case, I'm not doing it. Why? Because 0 is already something false and 1 is already something true. I could say equals 1 here, but it's redundant. It's not necessary because 1 is already true. In this chapter, we're going to be creating our player. The first thing we're going to do is create our player class, which I'm going to create here. There we go. So first thing I'm going to do is import Pygame, import math in case it's necessary. So let's get started by creating the player class, and let's define the init method, and let's define where the player will be located. So I'm gonna place the player in the middle of the screen, you know. So let's define the X position of the player as being the window. Also, we need to import our settings, so we can use these values here. Window width divided by 2. Also, self.y window height, this time divided by 2. This will make the X and Y positions of the player to be in the center of the screen. The player will be a little dot on the screen. It will be a little circle, so we need to define a radius for it, and I'm going to define it to be like 3. It's a good value for us. And now let's try to render it so we can see. Render, let's ask for a screen, and pygame.draw.circle, and let's draw it in the screen. I'm gonna draw it in the color red, and let's place it in the X position, the Y position, and let's define the radius that we just created, which is gonna be 3. So yeah, now let's try to run this. Let's instantiate the player here. First we need to import. Let's go. So after we render the map, we are going to be rendering the player in the top of the map. So yeah, let's see if it works. There we go. You can see a little dot over here, which is the player. Well, if you try to increase the radius of the player, it will make it bigger. But I guess 3 is a good size for us now. The next step is to create a line that indicates the direction that the player is looking at. For this, we need to draw a line that goes from player's position. So let's draw this line here, and the color red. So it goes from the player's position, and it ends in the point where he is facing. But we don't have this information yet, so it would be something like self x plus some value that we don't know. I don't know which kind of value this is. Self dot y plus another value that I don't know. This value is what is going to define where the player is looking at. So let's just use 50 as a placeholder for just we see what happens. As you can see, the line is going from the player's position to 50 pixels horizontally, and 50 pixels vertically. What we really want is when we press left or right on our keyboards, this line rotates around the player, showing where he is facing. But for this, we would need to use some trigonometry. So I drew this little diagram that shows where the end position of the line would be. Consider A as being the rotation angle we already have on the player class. So the only thing we need is to use the cosine of this angle, the sine of this angle, because these values are basically x and y positions of the end position of the line. So going back to our code, instead of 50, we could use math.cosine of a particular angle. But I didn't define the angle, so let's just define it here. Self.rotation angle equals 0, and now let's put self.rotation angle, and here also math.sine of rotation angle. So if you run this, you're not gonna see anything. Why? Because trigonometric functions such as sine, cosine, and tangent have a range of -1 to 1. So 1 pixel is not enough to us to see. So let's increase that by multiplying this result with some kind of value. I don't know, maybe 50. Let's see here. Now let's run it again, and as you can see, you have a little line here that shows where the player is looking. If we change the initial angle, let's put here like 90 degrees, but of course we need to convert it to radians. So let's do this little calculation, and as you can see, it starts on 90 degrees. Of course it starts going downwards because the y-axis on Pygame is inverted, so actually y increases by going downwards. If we start by, I don't know, 180, of course it would go like this, 45 degrees, something like this. And as you rotate the angle, the player will also rotate the line. First of all, we need to figure out a way to move the player according to where he is looking. So let's suppose that the player is this little ball here, and then he's looking in this direction here. It forms like an angle of 45 degrees, for example. And how would we make so that the player, when he presses the up arrow key on the keyboard, it moves in this direction? So it's very simple. We just need to remember from our high school classes about sine and cosine and tangents. The famous SOHCAHTOA. You might remember this from your high school classes. So what we need to do here is transform this into a unit circle. Let me try to represent this. So this is a unit circle. Why it's called a unit circle? Because it goes from 0 to 1 in the x-axis and 0 to 1 in the y-axis. And this is very useful because in the x-axis we have what we call the cosine function of an angle. And the y-axis we have the sine function of an angle. So we have this player here looking at this direction with this particular angle, and how do we make he move in this direction? So let's imagine that this arrow here is a vector that represents the movement of the player. I'm gonna call this the move step. So we need to decompose this vector into two components. I'm gonna draw here the x component of this vector. This is the x component of the vector, which I'm gonna call A. And this is the y component of this vector, which I'm gonna call B. By decomposing the vector, we can move the player accordingly on each axis of the movement. So first of all, let's define the sine and cosine of this angle. what should be the sign of the angle, which is 45, and you see 45. So from Katoa, you remember it's the opposite over hypotenuse. So the opposite of the 45 is the b. So let's put b over the hypotenuse is the move step. The cosine of the angle is the adjacent over hypotenuse. So adjacent is the letter A. So A over the hypotenuse, which is move step. Alright, so we need to solve these equations for A and B. So in this case, B is going to be, sine times move step. And in here, A is going to be cosine of the angle times move step. There we go. We have these equations here that describe the movement of the player in both axes. The A represents what the player is going to move in the x-axis, and the B represents what the player is going to move in the y-axis. So we just need to implement this in our code, like self.x plus equals A, and self.y plus equals B. That's it. So now that we just figured out this, we need to create some more attributes so we can finally make the player inputs. So let's define here turn direction. This variable is going to be responsible for telling us if the player is rotating to the left or right. If it is 0, then the player is not turning anywhere. If it's 1, then the player is rotating to the right. If it's -1, it's rotating to the left. Let's do the same thing for walk direction. If it is 0, then the player is not moving anywhere. If it's 1, then the player is moving forwards. If it is -1, then the player is moving backwards. Alright, so another thing we need is to set the move speed. The move speed is the speed of movement of the player. So let's put like 2.5, it's a good value. And also let's define rotation speed, which is like the sensitivity of the rotation when the player rotates. And also we need to convert this to radians. Now let's finally get some user input. We need to create the update method. This update method is going to be called every frame on our game, and every frame we want to store all the keys that are being pressed by the user. In every tick we also want to say turn direction equals 0 and walk direction equals 0, because if the player is not pressing anything, it's going to be 0 because he's not doing anything. But if the player is in fact pressing some keys, such as pygame.key right, so if the player is pressing the right arrow key, oh my god, so turn direction will be -1, actually 1, sorry, because he's going to be turning right. If the player is pressing the left arrow key, then the turn direction will be -1 because he's going to rotate to the left. Alright, this is like where the player is looking. But now let's make where the player is gonna move. So if the keys that are being pressed are the pygame.key up, so if I'm pressing the up arrow key, then I'm going to move forward. So walk direction will be 1. And if I'm pressing pygame.key down. If I'm pressing the down key on a keyboard, then I'm going to move backwards. Self dot move walk direction will be -1. Now we need to rotate our rotation angle when the player is pressing the correct keys. So let's go back to 0 here. Let's just define it to 0. And let's now say self.rotation angle plus equals self.turn direction, because if turn direction is 0, then rotation angle will be increased by nothing. And we multiply this by the rotation speed. So if it's 0, then rotation angle plus 0. If it's 1, then it rotates by the rotation speed. If it's -1, then it decreases by rotation speed, because it will be negative. So now we have a little problem. When we move forward, how are we going to move the player to the correct direction he is looking? So as we saw from this sketch, we can only just do this. So let's try to implement this. Self.x plus equals math.cosine of self rotation angle times the move step. But how are we going to define this move step? So let's define it over here. Move step equals, what is the move step? Basically the length of the movement of the player. It can be self.move direction, actually walk direction, sorry, times self.move speed. We pick the walk direction if it's 1, 0 or -1 and multiply this by the move speed, and this is basically the amount of movement that the player is going to move. But we need to decompose this vector into constants and individually add them by the x and y positions of the player, just like I'm doing here. Self dot rotation angle times the move step, and there we go. Now if we run the game and try to move the player, nothing is gonna happen. Why? Because we're not calling the update method of the player. So let's call player.update and let's see if it works. As you can see, I am moving around here, and look at that. If I press left, it rotates to the left. If I press right, it rotates to the right. If I press up, it moves forward in that direction that I'm looking, and if I press backwards, it moves backwards in that direction that I'm looking. Just to clarify, I forgot to record this when I typed clock, which is the Pygame clock, which I can set the game to be at 60 FPS at every tick. So that's why if you remove this, maybe the game should run like too fast, you know. So make sure to implement the clock if you're using Pygame, so the game can run at 60 FPS or something reasonable. I don't know, it's up to you. So in this chapter we're going to create our Ray class. Let's create a file called ray.py, and in here let's import math and Pygame. And now let's create our class, the class Ray. This class will be used to define a single ray. Let's create the init method. So every single ray should have an angle. The ray should point to somewhere, so we need an angle. And also the ray needs to know about the player, because it's from the player's position that the ray is going to be casted. So that's some information that we are going to be using. So self.ray angle, we're going to be defining the ray angle to be the same as the angle. Self.player equals player, and That's it. So what is a ray class without the cast function? So let's define the cast function. This function will be used to cast the ray, and this will be basically the core function of our project. But let's leave it for later. Let's not implement this yet. Now let's create the render method. So this method will be basically the same thing as we done in the player's render method. We just have to draw a line on the screen with the color red. That goes from the player's position, self.player.x, self.player.y, and it goes to the player's position plus cosine and sine of the ray angle. So let's do that. Self.player.x plus math.cosine of the ray angle, self.ray angle. But of course this is not enough, because cosine goes from -1 to 1, and this is not too much for us. We need to multiply it by some kind of constant, which will be 50 for now. And for the y, self.player.y plus math.sine of the ray angle. Of course, times times 50. That's it. But notice that this will be temporary. Let me type here temp. Because of course every ray isn't going to have the same length. It's going to have to find walls and stuff. So this is going to be our class for the moment, and in the future the only thing that we're going to do is to implement the cast method, which will be used to find walls in the ray's path and calculate the distance that the line should travel. So this is an optional step, but again, I like to create it because...
Hello guys, I came here from the future to say that this method isn't actually optional. You guys must implement this. It's actually required. I said in the video that it is optional, but it's not. It's required. So please implement it. Otherwise, you're gonna have problems in the future, so trust me.
So this function takes an angle in radians as input and returns the equivalent angle within the range of 0 to 2 pi radians. First it calculates the remainder of the input angle divided by 2 pi using the modulo operator, and this ensures that the angle is within the range of 0 to 2 pi. Then it checks if the resulting angle is negative. If it is, it adds 2 pi to the angle to bring it within the desired range. Finally, it returns the normalized angle. And where should we implement this? We're going to be normalizing the angle that we pass here. Again, this is optional, but it makes easier to debug because the angle will always be between 0 and 2 pi. And yeah, that's it. Now that we finished the implementation of a single ray, we need a class to handle a collection of these rays and to do several things, such as casting these rays, rendering the rays, and rendering the 3D walls. So what should be the name of this class? Of course, it would be Raycaster. And I'm going to create a file called Raycaster, and let's import Pygame, and let's import our settings because they are going to be used. Settings, import everything. From the ray, we're going to import the ray class. Create the class Raycaster. And let's define the init method for it. So the thing is, the Raycaster class is going to store some rays. So let's self.rays equals an empty array like this. And also the Raycaster class should know about the player, because the each ray also needs to know about the player. So we pass the player through the Raycaster class, and the player will be passed each ray inside of the rays array from the Raycaster class. So self.player equals player. So now let's create the most important function of this method, which is the cast all rays. So this method is going to cast every ray from the rays array. So basically, in our ray class, we have the cast function. Basically, what this function here will do is it will trigger the function cast from every ray inside of the rays array. But we're gonna do this later because I'm gonna explain something first. So let's do the render method first. Self screen. And what's gonna happen here is we're gonna loop for every ray in the rays array. I'm gonna render every ray passing the screen just like this. So the algorithm for the cast all rays function, it's gonna be very simple. Let's imagine that the player is this little green dot over there, saying the player is looking at this direction here. And let's imagine that there is a wall over here. So there is a wall over there, and what is gonna happen is the player has a field of view, just like this, right? We all know that because we have implemented it. So the field of view of the player has a total of 60 degrees. And what is going to happen is that the player is going to cast a bunch of rays there we go. So the player is going to cast all of these rays, and as you can see in this example, the player casted 1, 2, 3, 4, 5, 6 rays. So as you can see, the player has a 60 degrees FOV, and well, each ray has an angle between them, so the angle between the rays are the same, as you can see here. So the angle between the rays, it's going to be the field of view, which in our case is 60 degrees, divided by the number of rays. So let's make this count. How many rays we have? 1, 2, 3, 4, 5, 6. The field of view is 60 degrees. So 60 degrees over number of rays, which is 6. And this will give us 10 degrees. Each angle here is gonna be 10 degrees, summing up to 60 degrees. So how would we implement this in our code to make it to work? Well, the thing is, let's redraw everything. Let's imagine that the player is this little ball. It's looking in this direction. It has a field of view like this. All of this is 60 degrees. So now let's imagine the player is here at the origin, and the player is making 90 degrees within this origin. Okay. So remember that the y-axis increases by going downwards, so it makes sense this is 90 degrees because y is going downwards. So yeah. So how are we going to do this? We're going to be casting rays from this side, and we're going to go from here like this, like this, like that, and it's gonna finish in this side. But the problem is, we need an angle. We need an initial angle for this ray here. And of course, this side is 30 degrees, and this side is also 30 degrees, because this little line here, the middle line, divide this FOV into halves. So why this information is useful? Because we know that the player is 90 degrees, of course. I mean 90 degrees only in this example. Of course it could be any angle, but I'm just showing you this particular example. So this is 90 degrees. Okay, so the ray, what is the ray angle? We need to find out what is this angle here. This mysterious angle is the initial value that we need to find to cast our first ray. So, well, this is very simple to figure out because we know this is 90 degrees, this is 30 degrees. We just have to pick 90 degrees and subtract by 30. And that's it. So we have a value of a variable called ray angle, which we're going to be creating later on our code. And ray angle has an initial value of the player angle, and we subtract it by half of the FOV, and then we get this little angle. So what's going to be next? So we need to cast more rays. So what's going to happen is we're going to be picking up this little angle and we're going to be increasing it by a little bit like this. So we have a new ray angle, and now we can cast a new ray within this little angle, actually this big angle here. And now we are going to be increasing this another time and then casting another ray, and then we're going to be increasing this angle again. Remember, this is only one angle, like this giant angle here. It's just being increased, and then I'm going to cast another ray, and then we're going to increase again and cast another ray. So as you can see, this is the algorithm that we need to implement. We increase and cast, increase the angle and cast. So what is the value that ray angle is being increased by? Well, you see, all of these values are basically the same, and they are literally the same value that we just found before, which is the angle between all of these rays. So we just need to increase by FOV divided by number of rays. So FOV divided by num of rays. So the algorithm is very simple. The first thing we need to do is define an initial value for a ray angle, and then we increase by the we cast, of course, actually I forgot. We need to cast the ray in this angle, and finally we increase the ray angle, and then we go back to the second step, casting the ray in this angle, and then we increase, cast, just like this. So going back to our code, we are going to define the ray angle variable, which is going to be self.player.rotation angle, which is the angle of the player, minus the field of view divided by 2. And after that, we need to go through the number of rays and create a ray for that. So ray equals ray, and then we pass the angle we just found, ray angle. We also pass the player because the ray class needs it. And finally, we cast this ray. And also, remember that we have this array here. We need to store every single ray inside of this array. Self.rays.append ray. And now finally, we are going to be increasing, making the third step, which is increasing the ray angle by FOV divided by number of rays. So ray angle plus equals the field of view divided by number of rays. And now we are safe to test this out. So let's define Raycaster here. Raycaster, of course. Let's import this from Raycaster. Import everything. I mean Raycaster, and we pass the player, and I mean that's it. Now we just have to say Raycaster dot cast all rays. And also we need to render, so Raycaster dot render screen. So let's run this python 3 main.py. So there was this little error, which was the problem here because on Raycaster this num rays is not an integer, and it makes sense because I forgot to floor it on settings. So remember to make it as an integer, or just to floor it like that, and that's it. So now we should be able to run it, and ta-da! As you can see, whoops, oh, there's a little problem here, and I know exactly what it is. So the thing is, we need to reset the rays before doing anything, because so what I'm trying to say in this part of the video is that we need to reset the rays array before casting all rays. What I can't explain is why the rays array is so useful. The idea is that in every frame of the game we have a collection of rays to cast and render. But when we go to the next frame, we need to clear the rays array. Otherwise, we would be appending elements to the array until our computer goes out of memory. And imagine, so in every frame of the game, we're adding, like, I don't know, maybe 30 rays to the memory, and the game runs at 60 frames per second. In every second we would be appending so much rays, so in that, I don't know, maybe in 5 minutes I don't know, the game would freeze because it's out of memory, and you know, that wouldn't be cool. So we need to clear the rays array before doing anything. Render, so we need to reset this. So now we should be seeing what we expected. As you can see, every ray is being casted. Of course, the rays are not actually being casted, they are just going in the direction that they should go. After all of this, it's finally time to understand the logic and math behind raycasting. Let's consider the situation where the player is here and there are some walls over there. Let's imagine that the player will cast a ray in this direction. How would we know if the ray found a wall or not? A simple approach would be to, in the direction of the ray, we check through little intervals if there is a wall or not on all of these points. What I mean is, we're going in this direction and we would be checking if there is a wall here and here and here, here, until we find a wall. Once a point finds a wall, that's it. We stop checking and go to the next ray. This approach is very simple, but it's very demanding for our CPU. So imagine having to check a bunch of different points like this for each ray. It's a waste of energy. A more efficient way of doing so is to only check points in some positions where potentially we could have a wall. As you can see, these points are the only points that we need to check if there is a wall in every tile the ray is passing through. For point A, we're checking the tile above. For point B, we're checking the tile on the right side. For point C, we're checking the tile above. For D, tile above. So how does it work? If you didn't notice yet, these points are checking intersections in the horizontal lines of the grid, as you can see for points A, C, D, and F. and also the vertical lines of the grid. These locations are the only locations necessary to find walls. As you can see, we would need much less points. Alright, so let's take a look at a simple overview of the algorithm we're going to implement. Here's the diagram I made to show the steps that we're going to follow. First, we'll have to check if there are any walls intersecting the horizontal lines first. After we find a hit, we store the coordinates of this hit. Now we have to check for vertical intersections, and after we find a vertical hit, we also store the hit coordinates. At this point of the method, we would have calculated two pieces of information. One is the horizontal hit coordinates and the other is the vertical hit coordinates. Now we have to calculate the distance of the player to both horizontal and vertical positions to find out which one is the shorter. The smallest distance will be the final distance that the ray should reach. If this didn't make quite sense to you now, don't worry, I'll come back to this later. Alright, now let's finally understand the raycasting algorithm in details. As you remember, the first thing that we must do is to check for wall collisions in the horizontal lines. Let's consider the following example. Imagine that the player is over there, and a ray is cast from the player. Remember, this time we're only going to check for horizontal intersections. So following this line of thought, the first horizontal intersection that happens is here, at point A. Since we're just counting horizontal intersections, point B will be skipped. The next horizontal intersection is at point C, and then at point D, and point F. Alright, then what do we have to do on our program now? First, let's find the coordinates of the first intersection point, which is point A. And just after finding it, we can figure out a way to find the rest of the points. Well, but why the first intersection, or in other words, the point A, is different from the other points? Well, because the player is close to it. This simple fact will change the way that we will calculate point A. So going back here, let's focus on finding a generic formula that will find point A for us in our code. Let me zoom in a little bit so we can see better. Alright, that's better. Let's consider we have the player's coordinates, which I'm going to call Px and Py. And also we have points A coordinates, which I'm going to call Ax and Ay. Let's draw some lines here. And as you can see, we have a difference here and here. And also the player has an angle. Alright, with this piece of information, we can figure out something. Now, let's remember some good old trigonometry and tell me what is the tangent of the player's angle. Well, the tangent of an angle is just the opposite side over the adjacent side. So we can just place what we found into the proper positions. Now, what we should do, should we solve this for Ax or Ay? Well, it depends on the implementation. For this implementation, I'm going to solve for Ax. So if you solve for Ax, you will get this formula, which is the first valuable piece of information that we're going to save. But notice something. We know where the player is. We know Py and also Px. The only thing that we don't know yet is Ay. So how do we find Ay? Ay is basically this y position here. What we can do to find Ay now? Well, the answer is, we can use some knowledge from the pixel to tile coordinates conversion thing that I just told you to do some tricks here. So if we floor the player's y position over tile size, we can get the tile row that the player is currently on. But if we multiply by the tile size, we can get the exact y position of Ay. However, if we just stopped here, point A would be actually checking if there is a wall on the tile below, which isn't what we want. What we actually want is to check if there is a wall in the tile above the point A. To fix this, we can simply subtract 1 over there. This would go up a little bit and point A would be checking the tile above. Why minus 1? Because y-axis increases upwards. Always remember that. For example, let's suppose the player has a position of 42 and 112. Doing the calculations, AY would be 95. Now here comes a question. What if the player is looking down? Well, it would change a little bit. So AY is over here again. And now we want to check for this tile. We can find it by finding the tile position, converting it back to pixels, so we can find the Y position of the tile that the player is in. But since we want the next tile, we add tile size to get to the correct tile. Now, for example, consider the player has a position of 38 by 76. Making all calculations, we would find that AY is equal to 96 in this example, which is exactly the pixel coordinates of the green tile we're checking. Well, let's summarize what we have now. First, we have a formula to find the X position of the first intersection point, and we also have two possible formulas that we can use to find the Y position of the first intersection point, depending on whether the player is looking up or down. Now that we found the first intersection points, we can find the others. You will notice that there's an offset between the X position of these points that have the same measure, which I'm going to call XA for now. And the same goes for the Y positions, and I'm calling them YA. A very important fact is that YA has the same size as the tile size. The player still has its angle, and according to geometry, this angle repeats itself like this. The first thing that we can find is YA. That will be negative tile size if the ray is facing up, and just tile size if the ray is facing down. Think of XA and YA as being values that will be added again and again so we can reach the next intersection point. For example, we just found AX and AY. Now we need to get to CX and CY so we can check another tile. We do that by adding XA to AX so we can get to CX, and add YA to AY so we can get to CY. Now it's time to find XA, and we're going to do this by using some trigonometry again. Just replace some values in the tangent and we will get the formula that defines XA. Again, let's recap. What do we have now? We have two possible ways to find YA depending on whether the player is looking up or down, and also we have a formula to find XA. Well, if you thought that was over, I'm sorry, that was just the beginning. We still have to check for vertical intersections. Let's consider the same situation where the player casts a ray in this direction. But now we're checking only vertical intersections. The first point of intersection will be point B, and the second one will be point E. Since you guys already got the idea, we know that the first thing to do is to find the position of the first intersection point. So let's make some lines here. The player has an angle, and let's again use some trigonometry. And now, should we solve for BY or BX? In this case, I'm going to solve for BY because BX will be easy to find. And now we have this little formula to find BY. BX can be found like this if the ray is facing to the right, and like this if the ray is facing to the left. Now again, let's find the rest of intersection points. You will notice again that there is a difference in X that is the same over and over. And the same goes for the Y difference. If the ray is facing right, then XA will be tile size, and if the ray is facing left, then XA will be negative tile size. As we know, the player's angle repeats itself over and over, and we can again use some trigonometry to find YA. There we go. We have discovered XA and YA. Now let's recap and see what we've got. For the first intersection, which happens in point B, we've got two possible formulas to find BX, depending on whether the player is facing right or left. And we've also got a formula to find BY. Now, for the rest of intersections, we've got two possible ways to find XA and a little formula to find YA. Now that we found the formulas to calculate certain points that are used to find horizontal and vertical intersections, we need to understand how everything is going to work, step by step. Remember the diagram I showed you? When the player casts a ray, the first thing we need to do is check for horizontal collisions. So let's review how we find horizontal walls. Step 1 is to find the first intersection, which is going to be point A. We have discovered earlier these formulas to find AX and AY. Knowing this piece of information, we can check if there is a wall on the tile where the point A is. But as you can see, there is no wall. Since we didn't find any walls, we can proceed to step 2, where we're going to find other intersection points by adding XA and YA. If we add XA, we can get to CX. Now we add YA so we can get to CY. Now we check if there is a wall at point C, but there is no wall. So we can proceed to the next point by adding XA and YA again. And now we can see that in point D we found a wall. When we find a wall, we stop checking for intersections and store the hit position to memory. Going back to our diagram, we have done horizontal checking and stored the coordinates of the intersection. Now we need to check for vertical intersections. So the step 1 is to find the first point of intersection. Again, let's imagine the same situation, but now the first point of intersection is B because it hits a vertical line. We have already discovered that BX can be defined by two possible formulas that depends on whether the ray is facing right or left. And we also discovered that BY can be found by using this formula here. Now we check if there is a wall at the corresponding tile and find out that there isn't any wall. So we can proceed to the next point. And we do that by adding XA and YA to get to point E. And we have discovered that XA will have two possible values depending on whether the player is looking to the right or to the left. And also we know how to calculate YA, so we add this as well. And now we check if there is a wall at point E. And actually there is a wall over there. So we can store the position of the hit to the memory. Alright, going back to the diagram, we have done vertical checking and we just stored the position of the vertical hit to the memory. Now, after doing both horizontal and vertical checking, we need to calculate the distance found and compare the distance to check which one is smaller. So let's do this. Here we have all the points that we found. Actually, ignore the point F over there, it wasn't supposed to be there since it wasn't necessary to find it. So for horizontal intersections, we have found a wall at point D. And for vertical intersections, we have found a wall at point E. You don't need to be a big genius to affirm that point D is the point where the ray should stop. But how are we going to tell this to our program? Well, simple. We just need to get to the point that is the nearest to the player. To do this, we first calculate the distance from the horizontal hit position to the player. Then we calculate the distance from the vertical hit position to the player. Then we compare the distance to find the nearest to the player. In the case of this example, the nearest distance was the distance from the horizontal hit. So this would tell us where the ray should stop. And after all of this, we would have successfully casted a ray to a wall. If we repeat this whole process through every ray that the player casts, we would have a perfect Raycaster in our hands. Alright, so now that we just saw all of that, we can finally get to the code. So before doing anything, first let's create some variables here on the constructor that will tell us if the ray is facing up, down, right, or left. So what is facing down should be? It should tell us if the ray angle is greater than 0, and if it is less than math.pi. This means that the ray is facing down. Remember that the y-axis is inverted, so this, in a normal Cartesian plane, it would be up, but since the y is inverted, so this means down. Alright, so is facing up should be simply not is facing down. Now, is facing right should be something more like this. So you can do the math here, and you discover that this basically means on a unit circle, the interval, the range of angle that is facing to the right. And also, facing left should be not self dot is facing right. Simple as that. Next, we need to define two more variables that will store the final position of the wall hit. So self.wall hit x equals 0, self.wall hit y equals 0. Alright, now we can focus on implementing the algorithm for the cast function. The first thing we're going to code is going to be the horizontal checking. So let's first create a variable that will say if we found a wall in a horizontal line. So found horizontal wall. This is going to be false for now, since we didn't find any wall yet. And we are also going to create two more variables that will store the position of the horizontal hit. So horizontal hit x equals 0, and that's it. Now what we should do is to start thinking about the first intersection. So let's create two more variables that will store the coordinates of the first intersection. So first let's find the first intersection y. To do that, we need to remember from the previous explanation that we need to check whether the ray is going up or down. So let's check that. So if the ray is facing up, then the first intersection y will be something like this. Now, if the ray is facing down, then the first intersection y will be something like this. Now notice that the tile size isn't defined because we need to import the settings. Alright, now we just found the first intersection y, so we need to find the first intersection x. So first intersection x is going to be that formula you guys should remember. Alright, so everything seems fine, but we need a way to keep track of the current intersection point that we're checking. So I'm going to create two more variables here called next horizontal x and next horizontal y. The first value of these variables will be first intersection x and first intersection y. Because currently we're checking the first intersection point, but later we're going to change it to different intersection points. So now that we've figured out the first intersection, we need to continue checking by using the XA and YA things we just saw previously. So yeah, let's define them here as 0 for now. And yeah, you guys should remember we need to find YA first here for the horizontal intersections. So let's find YA, and you guys remember that if the ray is facing up, then YA is going to be negative tile size. And if the ray is facing down, then YA is going to be tile size, just like that. You see, it's very simple. We're just extracting the information we've got and placing it into the code. So yeah, now it's time to find XA. So XA, as you guys remember, it's going to be YA divided by math.tangent of the ray angle. Now here comes a tricky part. This is going to be a while loop. I'm going to explain this, don't worry. Basically, what I'm going to do here is I'm going to check while the ray is inside the window. This is going to help us because if the ray escapes the window, the program wouldn't, go forever trying to find walls.
Well, basically, this makes sure that the ray stays inside the window.
So basically, this is making sure we stay inside the window and the ray doesn't escape. So now we're going to be checking if there is a wall at a certain point, and otherwise we continue checking by incrementing the next horizontal x and next horizontal y. So this is a good time for us to use this method we defined on the map class. So first we need to get a way to access the map from here. I'm gonna start by passing the map here as an argument and defining it here in the constructor. But the ray class is being instantiated here in the Raycaster class. So we need also to pass the map here. Let's create the map over here, self.map equals map, and let's pass the map as an argument in the Raycaster. And finally, in the main function, in the main file, I guess, we pass the map here in the Raycaster. Now it's going to be fine. We have the map, and now we can use that function from the map to check if there's a wall in the next horizontal x and y positions. So just pass the next horizontal x and next horizontal y, and this should be fine. So if this is true, it means we found an horizontal wall. So we can define the found horizontal wall variable to true, and we store the horizontal hit by being the next horizontal x and the horizontal y hit, we store the next horizontal y. And then we break out of the loop. Now otherwise, if we didn't find a wall, we need to continue checking. So we increment the next horizontal x by xa, and we increment the horizontal y by ya. And that's it. Now we can finally test to see what happens. To test this out, we need to go out of here, and so that's testing the horizontal, checking. That's it. Now we have these variables here, the wall hit x and wall hit y. These variables are defined here because we're going to use them on the render method. All of this line here is useless now. Let's create a new one. And the idea is that we just have to draw the line from the player position to the wall hit position. Now, so let's define this here, self dot wall hit x. It's going to be horizontal hit x that we just stored after we found a wall, and self dot wall hit y. It's going to be horizontal hit y. Now let's run this and see what happens. Whoa, as you can see, it works. You see, it doesn't work for vertical intersections, but when you look up, it detects only horizontal lines. If you notice, the lines are only colliding in horizontal edges of the walls.
Alright, so now it's time for us to code the vertical checking. Let's comment this out. It's not necessary anymore. And now let's code the vertical checking. It's going to be basically the same thing as the horizontal, but different formulas and different names for the variables. So let's create the found vertical wall variable, and I'm going to call this and false. So vertical hit x and vertical hit y. So now we need the first intersection x and first intersection y. But for this, we can simply reuse the variables that we already created here. So let's do that. And well, the first thing we want to do is find the first intersection x. And you guys remember that we need to consider whether the ray is facing right or left. So if it is facing right, then first intersection x is going to be something like this. Otherwise, if it is facing left, then the first intersection x will be something like this. So now we need to find the first intersection y, and this is going to be something like this. Alright, so now we can set the next next vertical x and next vertical y variables. And the first value, it's going to be the first intersection x and first intersection y. Now it's time for us to find xa and ya. So let's do that. If the ray is facing right, then xa will be tile size. and if it is facing left, then XA will be negative tile size, but YA, it's going to be something like this. Alright, so now we need to do the same checking we did before. This is something like while it's inside the window. While it's inside the window, we are going to be checking for walls. Now this time we are going to use the hasWall method from the map, but this time we're going to use the next vertical X and next vertical Y. So if it has a wall, we can say found vertical wall equals true, and the vertical hit X is going to be the next vertical X that we found. And the same goes for the vertical hit Y. It's going to be the next vertical Y. Otherwise, if we didn't find a wall, we continue incrementing the next vertical the next vertical positions plus the XA and YA. Alright guys, so we've finished both vertical checking and horizontal checking. Let me comment this. So now there is no way to test this out because we don't know the wall hit that we don't know the wall hit positions. How to find this? Well, you just have to remember the last step from the diagram, which is going to be the distance calculation. So now it's time for us to do the distance calculation. And this is going to be the crucial step for us because this is going to be us finding out which distance is the smaller, so we can finally find the true position that the ray should stop, and we'll finally define the wall hit position. So to do that, let's first create two variables that are going to store the horizontal and vertical positions. Actually, the horizontal and vertical distances. They're gonna be 0 for now, but if we found a horizontal wall, then we can define the horizontal distance as being something. We should have a method like distance between. Let's create this method here. So let's create the method outside the class. Well, this is the method. I'm not gonna go through it because this is very simple. It's just a formula that finds the distance between 2 points. You guys should remember that from high school. So we can use that formula to find the distance between two positions. So the position that we're going to be passing is going to be the player position, and the horizontal hit position. So the horizontal distance is going to be the distance between the player and the horizontal hit. Well, if we didn't find a wall, then the horizontal distance is going to be a large number. It doesn't matter. Now, if we find a vertical wall, then the vertical distance is going to be the distance between the player and the vertical hit X and the vertical hit Y. Else, if we didn't find a vertical wall, then the vertical distance just going to be a large number. Now we have both horizontal distance and vertical distance. Now we can compare these distances and find the smallest one. So if the horizontal distance is less than the vertical distance, this means that the wall hit x is going to be the horizontal hit x, the wall hit y is going to be horizontal hit y. Otherwise, if this condition is false, it means that the vertical distance is smaller, and if the vertical distance is the smallest, it means that the wall hit x is going to be vertical hit x, and wall hit y is the vertical hit y. And that's it. Now, in theory, if we run this, it should work. Alright, so there's a problem here. Let me find this. Alright guys, so the problem was that I wasn't breaking out the loop here. This is very important. So now, well, you see, well, it almost worked, right? So there's some problems here, but I actually know what is happening as well. When I paste this while loop here, I forgot to change this to next vertical x, and it was x, yeah, next vertical x, and next vertical x here, and also next vertical y here, and next vertical y. Alright, so now if we run this, we can finally see it working. Well, but as you can see, when I rotate it a little bit, I got this error here, float division by 0. This is another problem that I have to fix, which is simply because I forgot to put an equal here. After doing that, we're going to be running this flawlessly, no errors at all. You can finally see it looks like a flashlight. It's very cool. So now it's time for us to turn this 2D representation in a 3D view, you know. Alright guys, so now we need to render the walls. And well, you'll be surprised on how simple it actually is. This picture represents how walls are projected to the screen. This is a wall. This is the screen, and this little guy is the player. Notice that between the orange lines, we have a white strip that represents the projected wall in the screen. Here we have some measurements. So to draw the projected wall in the screen, we need to know the projected wall height. But how can we find it? Well, you see, these measures have a relationship between them. They form a triangle similarity because the triangles formed share the same angles. So we can affirm that the projected wall height over the distance of the player to projection plane is equal to wall height over the distance to the wall. The projected wall is the data that we need to solve for in this equation. The wall height is a fixed value that it's very easy to find out, and the distance to the wall is simply the distance of each ray casted by the player. However, we don't know the distance of the player to the projection plane. How to find the distance to projection plane? The projection plane is just a fancy term to define the screen or the window. Here we can see our player's field of view, which is 60 degrees. 480 pixels is the width of our screen, and half of it would be 240 pixels. And here it is what we want to find.
the distance from the player to projection plane, which I'm going to call D. We can find out that D is going to be half of screen width, which is, in this case, 240, over the tangent of half the field of view angle, which is 30 degrees in our case. And this will result in a value of approximately 415. Now we go back to our giant formula. We shift things around and we get the projected wall height. Now we can use this piece of information to draw rectangles for each ray, thus generating walls. Alright guys, so before doing anything, we need to make sure that the ray has a way, we have a way to access the distance of the ray. So let's go here on the ray class, and back here let's define a distance value to be 0 for now. And when we hit any wall, we are going to define this distance. So if the horizontal distance is the shorter, that means the final distance is going to be the horizontal distance. And for vertical distance as well, distance equals vertical distance. Now we can safely access this distance value from anywhere. Alright, now here comes the part where we're going to be drawing the 3D walls. So first of all, we need a way to count the walls. So let's create a counter here. It's going to be 0, and at the end of this for loop we're going to be adding +1 for it. We can actually call this I, why not? So now let's put together all of the information we just collected so far. And first let's define the line height. This will be the line height for that will be projected into our screen. And we know from the formula that this is going to be the wall height, which we don't even have now, over ray distance times the distance of the player from the view plane, the projection plane actually. So we found that it was 415. But what is the wall height? Well, this value is actually user defined. We can define it to be anything according to our taste. So I'm going to be assigning the same value as the tile size, but it can be a value that you prefer. It doesn't matter. So let's begin by defining a place in Y axis to begin drawing the rectangle. This is going to be the window height over 2 minus line height over 2. And also we need to draw end, which is going to be the line height. Now we just have to ask Pygame to draw every line to finally render the walls. So let's create a bunch of rectangles on the screen with a color like green. And now we need the x1, y1, x2, y2. The x1 is actually going to be I times res. Remember that res is actually the width of each line, so we multiplied it by our counter so they appear next to each other, filling up the whole screen. And y1 is going to be the draw begin that we defined. x2 is going to be the resolution itself, because, well, x2 is the final x position to render the rect, so it's going to be the width of it, which is res. And y2 is going to be draw end. And that's it. Let's run to see what is going to happen. Whoa. Well, as you can see, it worked. But we're still rendering our 2D view. So let's remove it. So to do that, we just have to comment these two lines, and then, oops, actually on the render we need to stop rendering the ray. Yeah. Now we have a Raycaster, but it's not done yet. We need to make a few tweaks. Alright, so if we run this, you're gonna see the walls, very nice, but when we go closer, when we get closer to a wall, you see this fisheye effect. The walls are curvy like this. So when the player casts the rays, you can see that some lines are bigger, which will cause the lines on the sides appear smaller, causing the fisheye effect. To fix this, we need to stop measuring the ray distance from the player's position, but instead from the player's view plane. To find the value of this distance, we can use the cosine of this angle A here, which is the difference between the player's angle and the ray angle. We can then discover that the new distance is the old distance times the cosine of the angle A, and we can apply that to our code to fix the distance. So after the explanation, we just have to go here and multiply the distance by the math cosine, the cosine of that angle A, which is self.player.rotation angle minus self.ray angle. And this single line of code should fix the problem. Whoa, look at that. Now, as you can see, we just removed the fisheye effect from the Raycaster. At this point, we have this Raycaster, but it looks really weird because of this green color. We can't even see the wall corners here. We cannot even differentiate it. Well, yeah, it looks really weird. So let's change this color. The first thing we're gonna do is go into the Ray class here, and I'm going to assign a new variable called color, and I'm going to say 255 for it. Now we go to the Raycaster, and instead of green, we put in this here, we're going to put a ray.color, ray.color, and ray.color. This will be 255, 255, 255, which is white. Okay, so now let's add a color differentiation from the sides of the walls. To do that, we're going back here on the Ray class, and here at the horizontal and vertical stuff, we actually go here, and when the horizontal distance is the chosen one, we assign the color to a little darker tone, for example 160. Otherwise, if it's vertical, then self.color equals 255. Yeah, well, you can see now we can now differentiate from a side to another. And as you can see, we have some little glitches here. You see? Well, to fix this issue on this flickering here, it's actually something I didn't figure it out, but a way to fix this would be in here we put 0.01 instead of 1, and here as well. I don't know how to fix it 100%, but this makes it less glitchy. Now we need to add the light effect as if we were in the dark, and the further away is a wall, the darker it would be. So to add the depth effect at the end of the function here, we're going to do a little formula that will make the color change according to the distance of the ray. So it's going to be the light level over self.distance. Why light level? The light level would be a value that will define, well, the light around the player. Let's put 60 to see how it would behave here. Well, look, now it looks, oh my god. We get this error here because there will be a time that the color will be above the value of 255. So we need to clamp these. So if self.color is greater than 255, then self.color is going to be 255. And if self.color, I don't know why I put these parentheses here, right, is less than 0, then self.color equals 0. Now it's going to work. So the light level of 60 looks like this. We can change that, for example, to 10. This would look more darker, you know. You see, looks like a horror game or something. We can change that to a higher value, like 200. And this wouldn't make any difference, actually. So I think 60 is the perfect value. Now, for the final touch, we need to add a background image. So here I have a background image that we can use. To load this image, we just have to go and create a name for a background image. And now we just have to render the image here. Instead of filling the screen with black, screen.blit background image and the position 0, 0. Oh, this should be in parentheses. Now we have the Raycaster. You can change it according to what you want. You can change, for example, FOV. You can change to 120, for example. And you would get this very weird effect. It's very cool. 90. Looks really weird. And you can even change the map. Here we have the map. We can, I don't know, remove some walls. This is only the beginning. You can work to add some textures, add sprites, enemies, anything you would like. This video was more to show you guys the essence of the Raycaster. Alright, so I think that was it for the video. I'm sorry if my English was not that good sometimes on the video. I am still improving it. I hope I can get better the next time. I want to say thank you for the support on my last video. I wasn't expecting that huge success. That gave me the inspiration to make this one. If you want to support me, you can give this video a thumbs up. Or, if you would like to help me out, maybe you can, I don't know, buy me a coffee? Yeah, I'm just saying, you know, I'm just saying. And remembering that the GitHub repo will be in the description if you'd like to see the code. Again, thank you so much, and I hope I see you in the next video. See ya!